Welcome everyone to the Refrigeration Mentor Podcast and CO2 Monday. I'm your host, Trevor Matthews. And today I got a special guest, Phillip Walker from Arneg System. Phillip is the Director of Refrigeration and has been in the refrigeration and HVAC game for well over 20 years. And this guy knows what he's talking about, and he's been heavily involved in CO2. One cool thing, I met Phillip about 2 or 3 months ago at Atmosphere America Summit, and what a great event that was. I really liked your presentation there, but you mentioned that you have technology, patent in CO2 technology that we'll get into today, which I'm really excited about. Welcome, Phillip, to CO2 Mondays. How you doing?
I'm doing very well. Pleasure to be here, guys.
Awesome. Why don't we start off and you do a little introduction about yourself and Arneg and what's going on?
It's Phillip Walker. I'm Director of Refrigeration Solutions for Arneg Systems. If you haven't heard of Arneg, we got 21 manufacturing facilities worldwide. We've been building CO2 since 2005. We opened our doors here to the public in 2019, and we're building everything as small as 20 kilowatts right up to 300 kilowatts. So it's been a fun ride, and we're enjoying sharing our, all the little hurdles that we've gone through and all the more or less design iterations and expertise that we can share with you. So hence Trevor reaching out, and we thought it would be a great discussion point. There was a lot of discussion on Atmosphere about the heart of the system being the flash tank. And Trevor and I thought it'd be a great starting point to talk about flash tanks, how we go to market with flash tanks. And then if we get some time, we'll talk about our patent, the hot gas defrost.
Yeah, I love it. I'm excited about this because I'm still new to it. Even though I've been training CO2 for years, been involved in it, I got a lot to learn. And this is what I'm excited about. I'm excited to learn more about the flash tank because this is the major component, most important component of the system for quality control, quality liquid, stabilization of the system. And it's something key to understand. Why don't we start off with a little bit about the technology that you use to make sure that that flash tank is key to running a good CO2 operation?
So I think no matter if you're a technician or engineer designing a project, stability is the heart. So every project we begin for every customer begins with what type of flash tank. There's not a one size fits all. The days of working just with a horizontal or vertical receiver that we did, back in the R22s and all our HFC days, is not out the window. Those same principles apply, but we're getting now and more involved into designing flash tanks for different purposes. And I'll give you a snapshot. If we're doing a supermarket system with hot gas, depending where our evaporators are, our flash tank pressure is going to be at X PSI. If we're doing air conditioning, that flash tank is going to be at X PSI, which we'll talk about. The flash tank is going to change somewhat on design, and how we build that flash tank is going to change as well. And I got a picture that we can walk through on how that flash tank is constructed. Obviously, the flash tank stability, there's a lot of good valves out there that are being employed right now. Our most recent projects, we're using a certain type of valve, and typically that valve just marries up with a type of control system. I would say most systems now do have the valves that are being offered to stabilize the flash tank, but it's not just the valve, it's how you're constructing your your inlets and outlets, and then how do you want to treat your manifolds. So we're going to talk all about that today because I think this is really, really essential to any type of CO2 system.
Yeah, and I love it. And that's the key, that it's important for both technicians to understand as well as engineers and designers who's designing these systems, because I think there's a lot of new things coming out in CO2, even though CO2 has been around for over 20 years as well as over 100 and some years when it first started. But over the last 20 years, technology has changed at a rapid pace for CO2, and you guys have been involved in a lot of it. So I love it. I'm excited to hear this.
So if you want, I could share my screen.
Yeah, I'm just going to open you up right here and make
Perfect.
sure that you can share. There you go. And for anyone listening on the podcast, we'll do our best to be as detailed as possible.
So that's great. I will walk everybody through here. Okay. So let me know when you guys can see my screen.
I see your, it's a list, like your main Explorer. so it's not the presentation.
Oh,
It's probably
huh.
another screen if you have
Hold
two screens.
on. Sorry, guys. Moment. Stop share. We'll try this again. Technology is only as good as it works, right? So,
Yeah, I know all about it.
okay. Here we go. Can we see this?
Yeah, and all you have to do is do a presentation, or unless you want to do it in this mode. It's up to you.
Yeah, no, this is fine. Just like this. We're going to step through. So, Trevor, just to confirm, you can see the screen. You can see my
Yep.
flash tank up here.
Yeah.
So, guys, so here, let's start talking flash tanks. We have customized our flash tanks for several years now. And just to let you know, not all manufacturers go to market the same way. I can only speak to how Arneg Systems is doing this presently. So all our flash tanks are rated for 750 PSI. So if using, type L ACR Great Lakes copper, we're going to put a pressure relief on there of 650 PSI on the very top. And this flash tank is well protected. We're always going to use 3 or 4 optic eyes, which you can see here. But where we start differentiating in the type of drum from standard refrigeration is really take a look at these inlets and outlets. Flash gas, basically we're going to put it on the top. Here's our GC outlet or the tank inlet, and here's our liquid. So I think it's really important to understand what's coming down and how is this tank working. So in transcritical mode, I'm going to draw, I got a little picture here from Dan Foss. Let me bring it over. Can everyone see this?
Yep.
Okay. So here's a cutaway. If you haven't seen this yet, you can go or you can Google on YouTube Dan Foss. They did a great little presentation on what does a transcritical fluid look like. And what you're doing here is you're seeing this vapor pressure pushing against the liquid. It's really like I like to call it, it's a sludgy, like a sludge effect coming down in transcritical mode. It's going to pass through a high pressure expansion device. Imagine that high pressure expansion device is just like your thermal expansion valve that you've always been working with, but naturally it's operating at high pressure and has a lot of mass going through it. So part of that that's going to be produced as that mass is flash gas. Flash gas has always existed, in evaporators. Anything as you're flashing down through your synthetic refrigerant into an evaporator or your CO2 system, it's a byproduct of being produced. But hence, we're taking the whole system, running it through that device. We have a substantial more amount of that flash gas being produced. And at the same moment, the job now of this tank, since we're flashing all this gas coming through, is to really regulate pressure and start having that gas condense inside in transcritical mode. So the little droplets of that after that gas coming back after that high pressure expansion device, which I have a photo of next, it's going to start to condense. You're going to have those little droplets form, fall down, and start pooling and creating your liquid. And this is where we really get into different pressure ratings. How we go to market, and I think this is really important, is there's not one size fits all. And it's important to note, as you raise flash tank pressure here, you produce less flash gas because the difference across your thermal expansion or your high pressure expansion device is less. So when we're doing a standard supermarket with hot gas, this tank is running at about 480 PSIA. And this is when we're running in evaporators are standard. We're in a mechanical room, and evaporators are say lower, they're on a sales floor. When we start getting into a supermarket with we're in the basement, the evaporators are slightly above us, we're going to raise that flash tank. And what we're doing is we're just creating our greater pressure differential for everything moving in the system. So this is what we work with. If we're doing a loop system with electric defrost, our flash tank is going to be around 550 PSIA. And I would say between these two, it's fairly standard as we've seen in the industry. The tank is running between 500 PSIA and 550.
Yeah.
When we get into some air conditioning, we're about 607 to 610 PSIA. It's only because our suction temperatures are so much higher, right? So that's just a snapshot. I wouldn't say that's for every manufacturer out there, but if you're working on an Arneg system, this is basically where we're at and how we're designing our flash tanks, okay?
And do you know what I love about that, Phillip, is that you have on there air conditioning, because CO2 is in air conditioning. So I talk to
Oh
so many
yeah.
people that don't oh, CO2 in air conditioned, oh, the pressures. No, it's in air
We're
conditioned. Look, it's on their sheet. They're talking about it.
and you're dead on. I mean, we're doing a lot of mixed use buildings right now. And when you get into mixed use buildings, there's some more stringent codes. And bringing in a synthetic refrigerant may not be the best means for the developer, right? And you're sure as heck not going to bring in, unfortunately, another synthetic refrigerant. We're limited in propane, and you can't bring in ammonia for a mixed-use building. So we're left with CO2. So we're doing a lot of indoor air handling units with CO2 coils, and we're coming right off the rack, direct expansion. This isn't glycol, and 100% CO2, and it's going very well. The good thing about this is mixed-use buildings were limited as well in where we can put our gas cooler, and CO2 helps us overcome some of those hurdles and some of those obstacles. We're up to 12 stories right now where we're installing dry gas coolers. They're putting dry pavilions out, they fence off the gas cooler, and we're running piping 120 to 130 feet vertical run. We're putting P
Wow.
traps in there for oil, and this is working. We've done 3 so far at 120 feet. We're working on a design right now. We believe we can get up to 160 to 180 feet vertical run.
Wow.
So
Game changer.
some of the it's a game changer, and this is really because CO2, right? The higher pressure, we're running at about 985 pounds in winter time, and then in summertime when we see transcritical, we could be up to 1,200 pounds. And in Canada, at least, that transcritical somewhat is, it's not shied away from. We do a lot of heat reclaim, even throughout the summer. All supermarkets require dehumidification. So that dehumidification, we're bringing down the airstream really, really cool. We use the heat recovery from the CO2 system to temper the air and bring it up. So we supply neutral air to that supermarket space. So we're not shocking the customers. But all that movement of gas we just spoke about falls back here. This design. If she's not stable, everything we just spoke about in mass flow is not going to work at all. And the stability of the flash tank is the heart. If you have an erratic flash tank, if she's not stable, you're going to find that you're going to have erraticness there throughout your system. Okay? So this is how we're going to market with these PSIAs. The stability that we're seeing is significant, hence we can climb 12 stories to flash tank. When you're working on a flash tank, really think how the manufacturer designed it. Sometimes you'll see these 2 inlets. You might just have one on the very top. Well, if you're doing an air conditioning or maybe a CO2 system and you have a CO2 liquid pump, maybe you have a liquid pressure amplification pump like an LPA, you may have a lot less flash gas in the system. So you might just be pulling from the top of the tank. Or the top of the tank might be connected directly back to the compressors, almost like an intercooler design. These tanks right here for supermarket, we're producing 5,000 to 7,000 pounds in transcritical of flash gas. So we got to leave a little bit of room for that flash gas, because contrary to myth, it's not just being dumped in 100% into the suction header. That's being controlled. That gas on the top of this flash tank is regulating the pressure in this flash tank. And there's a valve doing so, which we'll get to. So that's why you have 2 inlets here. We're going to have one connected to a flash gas bypass. We're going to have the other one connected to either a backup emergency unit, flash gas subcooling, which we do, or hot gas defrost.
Wow.
Okay, which I hope we'll get time. Here's our inlet. We're coming down here. If you can see my cursor, coming down here from the gas cooler, going through a high pressure expansion device, coming right in here. Okay, and then here's my liquid outlet. So something really, really important, and this is going out to all the technicians listening right now that we found over the years. Stability is also insulation, and I can't comment enough on a good flash tank design in a mechanical room. You're going to need about 1-inch insulation. The bottom base right here should be blowing. You got a lot of sweating occurring down here. Check your base, check your bolts. If they're starting to rust, maybe you're missing some blowing in insulation. So we take these flash tanks, we blow in polyurethane down here. We actually weld them right onto the skid of our machine. And this is For a standard mechanical room, we have 1-inch insulation. A mechanical room that's going in a penthouse, we put 1.5-inch insulation. It's critical to the design of the flash tank. Improper insulation will cause an effect on your flash tank.
Yeah,
And how much?
I've had many people comment or ask me, like, because there's a lot of racks I worked on where they have accumulators, similar in a way. They're like, do you insulate them? Do you not insulate them? If you don't insulate them properly, like you're saying, you're going to run into issues. That's the big thing on any accumulator, any flash tank, or receiver. If you insulated a receiver before, you need to make sure it's done properly, and that's what you're stating here.
Absolutely, because think of the temperature running out here, right? So the days of 98 degrees is kind of out the window. That's out over here coming down from the gas cooler. We're flashing that down, just like you would with any type of DX system. She's running in here. If we're at 500 pounds, the temperature in here is 32 degrees. We got 32-degree liquid.
Yeah, that's
So
cool.
it's cold. And so if this is exposed in any means, and we've done a few projects where we've, some of the older systems out there, we've come in and the team has brought up to speed, insulation's wearing off. You'll have significant amount of condensation occurring on the flash tank. And that condensation will cause an effect on the older design flash tank. So just a little, caveat to think of. Insulation goes a long way. If you're seeing a lot of rusting water pooling down the bottom, maybe you're missing out on some insulation down onto the base, something to take a look at. It's going to help with your design.
That's a great tip. It's a great tip.
So nice and simple. Here's my first high pressure expansion device. Okay. So as we mentioned, 2 up here, let's say those are dedicated to flash gas. Here's my inlet. So here, what you're seeing right now is the Parker model. This is a high pressure expansion device of a project we're working on right now. We always put a strainer in front. This is a Yamis, right? This is critical. Remember, everything coming down on your stainless steel line, or maybe your K65 line, depending where you are in North America, is coming down, slamming into this valve. Okay? So we're talking, hey, what type of velocities are you guys thinking of? Well, slamming is the right word. We typically will not exceed 500 feet per minute coming down here as my run. Remember, you got 1 valve or maybe 2 valves here. It could be, the Carrel, the Danfoss, the Parker model. Regardless, they're all operating in a very similar fashion, fine-tuned differently for each one. But we got to respect that valve. The cleaner we keep that valve, she has a strainer here, the better it's going to run. Don't forget, this valve is probably the second most important part in your system. The first being the temperature sensor that controls it. Don't forget that little $20 temperature sensor you're putting on the outlet of the gas cooler that's driving a lot of the algorithms to control this valve, okay? So we always put a strainer there. The strainer, you got a bowl valve over here, you can tie off, you can open the strainer and clean it. When we're doing mixed use buildings, I can't tell you the first 2 projects we did, how critical that strainer was. Because if you're going up 120 feet, and the boys are welding all the way up, you got a significant amount of debris that could come back down. Well, this strainer saves the valves, right? So this is something we always do in our design, at least. So
Yeah, and
remember,
I talked to a lot of technicians who were doing it about 10 years ago, installing some of the first systems, and they said it was like night and day to the way they do it now, because they weren't as cautious about it. You know what I mean? Because they were used to doing supermarket work where you get away with a lot of stuff. With CO2, you don't get away with as much, especially with dirt in the system. And they were losing high pressure valves or flash gas bypass valves, is getting dirt stuck in it and causing damage, and then the system's down. So that's real cool that you add a strainer before that valve. That's so key. Awesome.
Absolutely. And we even go a step further. So don't forget, we got all high. This is all our high side right here. We could have 1,200 pounds. She's flashing down low side here. So this is why you see some K65. Our new design with our flash tank manufacturer, this is now all stainless coming in right now. Just on the terms of manufacturing, it's easier for us to put a socket weld here and come out completely in stainless. So just to say, if you're working on one of our systems, this whole line here is stainless, doesn't mean it's all high pressure. This is really the high pressure side. We're flashing down. This is the side that we're at that, say, 525 PSIA, 32 degree Fahrenheit coming in here. And then she's flashing condensing inside the flash tank. So this is what this valve is looking like. We like this valve at a point that's higher. I know you might see the valve a bit lower, but for us, with the way this flash tank is designed, you can see it's slightly higher than the inlet. We do that purposely because we work on basically the same principle as a water column, right? So if you can see my cursor, we're going to say, hey, we got liquid maximum to about right here. If we have liquid up here, we're going to be problem because this is our static area. This is our flash gas area. So we're going to have liquid to about up here. We like to put it up so she's raised primarily to the same point on the top of the flash tank. Typical flash tank for us is about 90 inches in height. When we do industrial, it's slightly higher, or we even do 2 flash tanks. And I know that might be a big question mark to a lot of the folks listening, but we do winter summer mode. That's becoming, we did a test run becoming more popular. It just makes sense. We live in this crazy environment called Canada, whereas Trevor could probably state the last couple of days, we've actually reached 100 degrees Fahrenheit. And last night we dropped down to, I guess it was 48 degrees Fahrenheit. So yeah. we see a big variation. Erraticness in that variation is responsive in the flash tank, which is responsive into all your case temperatures and everything. So something we've started to do is put 2 flash tanks, second one smaller, and then we thermal siphon between the 2. And realistically, what's happening is, depending on the mass flow requirement, we can pump out systems, and because we need less mass throughout winter months. And this improves the valve responsiveness, because don't forget, we're sizing systems based upon a worst case scenario. Well, as you walk into any mechanical room with a CO2 system in wintertime, you'll say, well, there's only 1 or 2 compressors running, right? It's just because of the way at this moment we're all sizing systems. So we've taken it a step further, add a second tank, smaller valve that we can change over to winter months. So it gives a better control over the flash tank throughout very cold winter days, because some of the areas that we deliver these machines, we honestly see guys like minus 25 to minus 30 degrees Fahrenheit at certain periods of the year.
And so that would be really good for control guys to understand, because at first you would think, oh, this is really difficult. You get 2 flash tanks, you get 2 valves, but it will be all in the programming, where I'm assuming that it hits a certain temperature and then it'll switch the whole system over, and it's done automatically. It's not like something you have to go in and continue to adjust. I assume this will be all built into programming, so it happens on its own.
You got her, and it's been very well received to this point. We got 1 system up and running, another in pilot, and basically you have a manifold with some valves with a Belimo actuator. So the guys have been working with this for years, this type of technology, two-way Belimo actuator. It's just now it's stainless steel. So as we go and we split condensers or split gas coolers, right? We split it in the same type of theory as we did with old condensers.
Yeah.
We can change over the manifold, because now we have a lot less mass flow requirement to satisfy the net refrigeration effect of the display cases. And we can't forget as well, cooler environments, drier environments, we have a lot less latent load for infiltration for the display cases. So Arneg provides display cases as well. And our maintenance on our suction temperature is far easier throughout the winter season, because the store environment is much drier. We're at a very, very low dew point. So there's a lot less infiltration or vapor pressure migration for the display cases. So suction maintenance is much easier. And we've said, hey, we can move that over to maybe keep this flash tank full, move it to a secondary flash tank with a smaller valve, because we need less mass flow. And the success has been outstanding in terms of that. Let me complicate things a bit more.
I love it. I love it. This is great.
So here's our flash tank. We just spoke about all this right here. Here's my gas cooler outlet right here. So now I got a secondary valve. What's going on here? And this is a typical setup I think more and more manufacturers are going through. We just spoke about this valve is the heart of the system. Well, it only makes sense to put a secondary valve in place. This is a dormant valve. That's why there's no strainer on it. This valve, all our systems have a secondary high pressure expansion valve, which in the event of failure, you unwire this valve, you pop the wire back on here, and the system's up and running while you source another valve. You just ball valve this line off right now, ball valve this line open, and the system is back and operational, and you're sourcing your valve. With stringent, I should rephrase that, with long lead times in the industries, it's been some of the technicians' worst nightmares where they have critical failures, and they're trying to source parts, trying to maintain the system going. When you have a supermarket, you lose this valve, it's a critical failure. Common process was to put a ball valve with a bypass. Well, we had technicians in our testing. We have a laboratory, just for anyone listening on. We have a laboratory where we test racks, controls, and cases. And common industry practice was you put a bypass with some ball valves. And if this valve failed, you crack open the ball valve, so your wrench and yourself is basically mimicking this valve. A lot of the times what happened when we were doing so, if we weren't careful, we're losing gas. We're opening up the relief line. And we thought we can make something a lot better. About 24 months ago, we said, this is so critical. For the cost of just adding this line, it's insignificant. It was actually costing us more money if we looked at maintenance and serviceability if this valve failed, theoretically, than adding the secondary valve. So we added it in. It's a safety feature, all our systems. And I know a lot of people.
I love that, Philip, because that's another game changer. You're willing to put more money into the system, costing you more money to help your customer out in the long run. And that's so important, because I've heard of this multiple times. I've talked to many technicians where, well, I lost my high pressure valve and I can't source one for a day or two. I had to pull the whole store, put it all in reefer trucks, and the store's down. You know what I mean?
Yeah.
You can't have that. And this design here, and for anyone who's listening, it's a vertical flash tank. At the top, you have a couple of flash tank inlet outlets, and then the next hole is for the gas cooler. And the gas cooler setup is a parallel setup with two high pressure valves. Super cool. I like this.
So the interesting thing here is automatically as a manufacturer, you think right away, as you just pointed on, additional cost. We built 39 systems like this last year. All customers welcomed it. To the point you just mentioned, they are willing to pay for the small substantial increase to the overall capital cost of the overall system, as opposed to ever be in a situation where it jeopardizes their store environment. To close one case is significant for them. Imagine losing, as you just mentioned, half of your store, right? It's just unheard of. So this made a lot of sense to us. And then let's go through this. This is now a typical subcooling system, and this is why I threw it in. So we got the high pressure expansion devices here. We're coming down here. We're going to go through a plate heat exchanger, or we do expanders. When we have air conditioning, basically the air conditioning suction side is coupled with the refrigeration liquid side, almost the same principle of a old school liquid suction heat exchanger. Except we use a special heat exchanger to expand the suction side. We get good subcooling out of that, and we drive the heat into the air conditioning side. This is a typical design where we're using glycol or water or any other means, not flash gas here, to provide additional cooling to the gas cooler outlet side. So gas cooler comes in here, then we're leaving out over here, and we just got a bypass. Simple as that. So if we don't need this additional plate heat exchanger to provide any additional cooling, we're just going to go down like that. We're going to bypass it completely. We got a check valve over here, and this is what's really important in CO2 systems. When we do a lot of speaking on CO2, I think when we're training in front of the machine, the common question is typically insulation and check valves. Gas wants to migrate. CO2 wants to migrate. So any type of circuits that you're working on, and you believe that they're going to become pump out, or we call them dead circuits, that you're not going to be used throughout that certain time of the year, really consider, if they don't have them, a check valve, because gas is going to migrate. Even in oil separators, if you have suction groups and you have multiple separators coming into a manifold, if those separators don't have check valves, gas is going to migrate backwards and is going to condense in those inoperable separators. So hence check valve, we don't want gas coming through there. And we're going to come right out and we're going to feed our high pressure expansion device here. Okay. Trevor, any questions on that?
No, I think that's perfect. It makes a lot of sense to me. And what I like about this, it's changing the way it's been done, and this is how I love what I love about CO2. It continues to get better and better and more evolving even more. So I think it's pretty cool. And when you said you use for that plate heat exchanger water or glycol, is that correct?
Yep.
And that would come
Yeah.
from what source again? You might have mentioned it, but maybe I missed it.
Yeah, so building glycol loops, especially mixed use, is readily available. So
Mm,
typically, and think about this when you're working on your projects, right? CO2 is a lot more efficient if we approach it holistically. I think the days of mechanical unification are in front of us. Store are getting smarter. We're talking net zero. I think we're taking off our hats and trying to approach things in a different way.
yeah.
So glycol loops are readily available, throughout several areas in North America. We're doing radiant floor heating to even plant growth, right, with glycol loops and plate heat exchangers. A lot of the time, that returning temperature from the glycol loop maybe is being used for an air conditioning circuit or plants or LED cooling, right? Um, it's typically after it's heated, it's coming back at a temperature still lower than the gas cooler. Well, we can take that temperature, say if it's 85 degrees, and heat it and provide some cooling, because maybe my outlet on my gas cooler, it's a dry gas cooler at that moment, is 95 to 98 degrees. My glycol's coming out at 85, so we can knock off a few degrees from the gas cooler outlet. And I'll say every degree you knock off is significant impact to the system, significant impact to the overall performance and stability of the system. In water or glycol is something we enjoy because it's very stable. It's a very stable fluid to work with. It's very predictable. So
Yeah, and I
something.
and I love that when you look at a CO2 enthalpy diagram and you see when you start to drop that temperature of that gas coming down, it makes a world of difference in the amount of flash gas that's going into the tank. So it's super neat that you built this design.
Yeah, and it's becoming more and more popular. We're working on a design right now where we're going to have an internal quote unquote type of chiller. There's a large freezer floor will be warming, and that temperature coming back from the freezer floor, we can manipulate not only to provide heat recovery for the freezer floor, but to serve internal means within the
Wow,
refrigeration system.
that's
So
awesome.
subcooling, we can subcool it, we can cool it, we can heat. It's another point of all this that we just spoke about with mass flow. When we get crazy cold environments, is also gas cooler stability, which is something we're not touching on today, but we're talking about getting this cooled down, which is probably our point of conversation if we're, south of Georgia and beyond. But as we go north of there and we start talking areas in remote Canada or even Alaska, we start talking of how can we keep it above certain temperature, right? Because gas cooler, we can lose it if gas cooler temperature becomes too cool. So now in some applications, we're also heating to provide stable temperature throughout winter months. So this design, I know we talk a lot about, we're always been geared towards transcritical, but there's a whole other side to CO2 as well, how we're using it in very cold environments to very, naturally hot environments. It's a very interesting gas, I could say, in that
Yeah.
way.
And that's what I love about it because there's just so much uniqueness about it. Like, we're talking about, oh, we're worried about, oh, it's too hot outside. Now you're talking about worrying about being too cold. You know what I mean? So
You got it. Too
pretty
too
neat.
cold is not good. Contrary to maybe some myth out there, we get back to the heart of the flash tank, and the guys in Canada really don't dread the hot days. They dread the very cold days, and the cold days is when you can lose stability in the flash tank. And when we start lose stability, we start losing our delta P's in the system, right? So yeah, there's measurements measures that we put in place. Hence, this, if it's very cold outside, that glycol loop we were just talking about, imagine that glycol loop now we're heating off a low temperature discharge line going through plate heat exchanger and then heating up maybe that gas cooler outlet temperature coming back at a very, very low temperature, maybe bringing it up to 50 to 60 degrees Fahrenheit,
That's
right?
super awesome. I love that. Love that.
So what we're doing is we're allowing these valves to properly work as well, because what we don't want in certain applications is ever the control system to start permanently closing these valves and work more like a holdback valve or like a Flowcon A8 valves. They weren't made to do that. And when we start cutting off these valves because mass flow is so low, we start losing that pressure differential in the system, right?
But isn't that what most systems are doing at this point? Especially when you don't have this type of design, when it gets really cold, they are acting as that holdback. Or you know what I
Yeah.
mean? Because
So
you only have that valve there when it gets so cold
yeah,
out.
well, and that once again, it all goes back to how you're cutting the gas cooler up in cold environments. Like your circuitry for your gas cooler. In cold environments, we were working on a project this morning with a customer, and we have 5 circuits on the gas cooler. I think it's really intelligent how they wanted to do this, because they understood load is going to be so minimum at certain applications that they need a minimum percentage to circulate mass flow. Well, that just states that if the customer is willing to understand that, the design has to understand that as well, right? So hence, we can't have just that one big valve, because it is just going to close, cause a holdback. But every time you close a valve, what did you just do? You just completely shock the system. You stop flow in the system. This is your primary valve. Here's your gas cooler, your primary valve that's providing, that at this moment, that very cool liquid, because we're in subcritical, coming inside the flash tank. If we start closing valves, we're starting to diminish that effect, right? And we're starting to
Yeah.
diminish the effect of those delta or those pressures. I'm just going to skip back here, that we want to maintain. Becomes even more difficult to maintain that. So if we tack on hot gas defrost and all these other things at the same time, we start to lose that effect. So it goes back to, how are we going to create that, not only for a very hot environment, but how are we going to create it for a very cooled environment as well?
I love it.
So what we have here, I thought this is a total different piping strategy. So we're looking at coming from the gas cooler before and coming into this inlet. Now this is the same drum, but here's our flash gas bypass, right? So same type of valve. This is a flash gas bypass valve, or maybe you've seen, like a CCM TS or something like that. All the valves are working on the same principle. This valve is driven by the pressure in the flash tank. It is an extremely important valve. We lose this valve, we're going to lose the pressure in the flash tank, and we lose all those critical pressure points that we just spoke about. So as you can see here, the flash gas, here we're going down, and then here is the suction manifold for the medium temperature compressors. The gas here isn't being thrown in 100% into that suction manifold. It's being controlled, the quantity of gas, because the design right here is we're going to maintain a certain quantity of flash gas in the tank to maintain pressure within the head of the tank, this part on the top here. So this valve is working in complementary to this high pressure expansion valve right here. And on this vertical flash tank, you really need the 2 of them. You need a valve to regulate as a high pressure expansion device to form liquid inside this flash tank. And you also need the complementary valve here on the flash gas outlet side, okay? Now, what's really interesting about this, do you always need a controlled valve in a sense of non-mechanical for a flash tank? And I think some of the guys are going to go out there and go, yeah, well, small flash tank drums, like when we go down to 20 kilowatts, this valve isn't driven by a control system. It's a mechanical valve on there. We use a certain type of mechanical valve with a solenoid for emergency reasons, and it's driven as we put our set point, we adjust our pressure setting, and on a small 20 kilowatt system, there is no electronic valve driving that flash. The system's just too small, right? And we've had a lot of success by maintaining it like that, because small system, what we'll typically do is have a little more flash gas in the system. So that small 20 kilowatt system will have maybe a drum quarter of the size of this. our mass flow is like 2,000 pounds per hour. Imagine these systems are going into your local convenience store, more or less. So that just paints a picture how much load is on there. These little mini boosters, we call them. So this valve, to eliminate another point, instead of building redundancy on it, we put a little mechanical valve, and she works really, really nicely with a solenoid.
And so that valve, would it have some sort of orifice in it that is regulating at that specific pressure? Because if you say like you have a solenoid type of valve on it, it's mechanical.
Yeah, it's
It,
mechanical. Yeah,
yes.
and working. So it has a pilot on it, right?
Okay.
And it's working like a whole back. And then we have a solenoid on there for emergency regions, right? So
You just need
flash,
to, yeah.
you got her.
You need to
So
let
in
more
the
gas
event,
out.
you got her. Exactly. And that's the way. So we use the valve on very low systems, because very low systems, we completely pump out the low temperature. A lot of small convenience stores, right, have very low load, especially with all the great efficiency with display cases nowadays, the night curtains, lower light intensity, so less per BTU per foot. So we find throughout the nighttime period, low temperature, especially with the doors, you're at holding temperature. So we pump out the low temperature system. And then this valve, if the low temperature needs, because we don't have a bypass between the two manifolds, being like a load bypass, just in case we start losing load, this valve can open more, the mechanical valve, and dump a little more flash gas into the suction manifold of the medium temperature compressors, right?
Mm.
On the medium temperature side for those very small units. But quite the opposite here. This is much larger system, regardless of all the measures that are put in place. These types of tanks are used just to paint a picture for systems that are 125 kilowatts or 167 horsepower, more or less. This is standard large scale supermarket design. Our minimum load we're going to see throughout a nighttime is 20 to 30%. So the medium temperature is always running. We got a lot of those great open display cases for meat or produce. So always a good amount of gas being produced, and then managing that pressure inside here to keep that stability. So looking at the two valves.
Those 20, those 20 kilowatt systems, they're more just like a larger condensing unit design. So you put on
No,
a,
no, not at all. It's a picture it as everything we're talking about here, but just miniature. So it's still a booster.
okay.
Still got independent low temperature, transcritical side. We can still heat hot water. We do a lot
Nice.
of hot water heating out of that. We're not doing any heat recovery because not that much heat, but enough to gain more than a few degrees in the hot water for a customer. But you can pump her out. They're all loop designed, so there's no hot gas associated with those small systems, obviously. But you can pump out low temperature and keep that medium temperature running completely. So the low temperature is just isolated. And good little convenience store application. So here's the flash gas bypass. So everything we just spoke about. One of the first things myself as the designer, when we're going into a mechanic room, the points as a technician, my guys and myself, we looked at when we go into any mechanical room for one of our machines that we've had a call on, is really what we just spoke about. We look at the drum. How's she running? We look at the valve. Okay. Everything we just spoke here, these valves, high pressure, how the drum is running, how's the flash gas, 100% we start there. It's the heart of the system. Are these valves closing? Okay. Is my strainer blocked? So not only closing, is it opening too much? And I think that's something we don't talk about. What's going to happen if this strainer is dirty? What's going to happen to this valve? The system's going to drive it further open. So take a look at your control graphs, and if you've seen that she's been running at 30 to 40%, and suddenly there's a little hiccup in the piping, and now she's driving 60, 70%. That's an unusual occurrence, right? You might want to take a fine look on, is this blocked?
And that's a good tip for any technician, not only for these valves, but as well as like case valves. Because when you understand and you start working with more electronic valves more and more, and I see more and more of them out there, you'll start to recognize, okay, these valves are always running at say 60% or 50%, or like you said, 30%. But all of a sudden you see they're now running at 70%. you got to think something's going on. You recognize that. And the more and more technicians I see working on CO2 systems are recognizing patterns like that, because one great thing about CO2 system, you got pressure and temperature probes everywhere. And now you can really take a look at the data log and understand how a system's running.
Yeah, absolutely. And I think that's one of the key points you just hit it on there is on a CO2 system is the amount of availability. I remember when I first started, I was first exposed to some CO2 systems in the early 2000s in Quebec, and I was so fascinated that I could troubleshoot as a technician from home, right? And it was like to have all that at my fingertips. I didn't have to go out and say, "Hey, I got liquid logging and I got to do this," or "I got to turn on all my, my compressor fans and we're going to treat it like a flooded condenser for a couple of hours to get all the charge back." It's like that was removed. I had everything at my fingertips. It was just understanding what I had at my fingertips, right?
Yeah.
And hence our discussion today. So before we move on from the slide, some of the guys might be looking at this. You can see there's a filter here. This is my suction filter. All our machines have a bypass. See, this is why we got the two ball valves here. We valve off, and then you can easily change your filter cores without shutting down the machine. This is something we do on no matter how big or how small, any type of machine we design. You will not have to pump out the machine. You will not have to turn it off. You can valve off, change your filters, and then keep the machine going.
Okay, that's great. So what's Arneg's rules on the type of filter that goes into the suction filter? What do you guys recommend? And is there a maintenance procedure for that? I'm assuming there is, but what filters do
Yeah,
you use?
so in terms of who we're using, in terms of manufacturing, the industry right now, all due honesty, is what can we get?
Yeah.
So we're using a lot of the Emerson STS series, and the reason why we're using that is they're rated up to 680 psi. They're readily available. We're using the Emerson cores as well. They're readily available, and you can get them, off market, really nice. We're not using anything special, guys. We also work with Sporlan, so our liquid side, the standard RC filters, nothing unusual. Rules of thumb asking. If you're doing a big renovation, put some, really look at your liquid side and put some HH filters in there. CO2 humidity doesn't go very well, I think, as everyone has seen. So a good cleanup filter is always recommended throughout renovation. But besides that, Trevor, it's run of the mill. After we do startup, we recommend filter change with the first oil change. We recommend oil be, it's not just like a rule of thumb when to change it. We like an oil test. A lot of the machines as well will look for a 10 to 15 pound pressure drop across the filter or across the oil separator. So we know it indeed. It's time. I can't count the endless stories where we just are on autopilot. We change filters for the no reason of changing filters, right?
Yeah. Yeah, you don't have to do that. So I just meant, and that's a great explanation, of pleated filters or solid core filters?
Oh, solid core filters.
Solid core.
Yeah.
Okay. Thank you.
Yeah. Yeah. Is what we're currently using right now. But
Yeah.
most market filters are absolutely fine.
Yeah.
At least for our systems.
Yeah.
So here what we have right now, and I kind of like this, is you're starting to see it all come together, right? We just talked about this, and I think everyone can see that now, and it makes a lot more sense. Like the rack is starting to build out. So our two valves right here, one's redundant, flash tank, vertical flash tank. Here we got that flash gas bypass valve. Here we got our bypass, our suction filter. Here's our plate heat exchanger. Here's our suction manifold going back to the compressors. So starting to build it out. We got a lot more piping right now, but as we start taking a look at it, each individual section, as we just spoke about, once understood, fairly easy to work with.
Yeah. And I really like the way you did that. And this is the way you should be doing it in the field. So if you're new to CO2 refrigeration or even rack refrigeration, go get the piping diagram. Arneg would ship it with their equipment, I'm sure. Start from the compressors and start working your way so you know what every component is. Because at first, if you would have just showed us this, you got a bunch of pipes everywhere, it's hard to understand. And when you get to a system, I've been there before, and you look and I'm like, there's valves everywhere, there's pipe going everywhere, there's three-way valves, and it's intimidating. But you take that PID drawing, the the mechanical piping drawing, you look at it, okay, start circling things, or photocopy it for yourself as a technician and take a half an hour or an hour. Because when you understand the system, just like Philip showed us here, you're going to understand how to troubleshoot that system because you'll know every component, what they do, where they're at. So thanks for doing it that way.
Absolutely. So obviously a lot of these lines are insulated. We put stickers on them. And if you're ever working on a Arneg system, you need P&I schematics, refrigeration schedule. Typically, they're always provided with the rack, but we always have an electronic version. What we're working on right now is we find after a few years, obviously things go missing. I think that's just the nature of the beast of our business. We're working on a HMI with a QR code. So
Awesome.
Arneg Italy is already there. This has already been done. Some of our partners are already doing this. So imagine you walk in, there's a HMI on the rack. Everyone has a smartphone. The guys scan the phone. You hit our server here and you get the most recent information, not only on what we're doing, but then you have all the documentation associated with your system.
Yeah, and I love that. And that's so important. The key to troubleshooting any system, if you're a technician or even designing as an engineer, you need to understand all those components, where they are, how they work. It doesn't happen overnight, though. Don't stress
Absolutely.
yourself and overwhelm yourself. Philip been doing this for over 20 years trying to understand this stuff. And me, it's 18 years in the last 7 or 8 years on CO2, and I'm still feel brand new. So just find information, take your time, read it, and over time you'll start to learn more and more.
So here we go. We got our bottom liquid outlet. So fairly simple. As any type of design, we're going to liquid feed into a manifold. You might realize there's a few little caveats here that are different from a standard design, and that's done intentionally for velocity. And what you're going to see as well, which is new maybe to an Arneg system, we put sight glasses, typically here, here, and on the manifolds themselves. It's because this is all liquid column. We want to ensure that we're getting good liquid out flowing properly into the manifold, right? So typical design, if you're asking velocity on our liquid, this is all done in K65. We're happy to work between 150 to 300 feet per minute is basically what we work on. But once again, bypass, there's your liquid shell. You can bypass it. And you'll see a little loop here. And that's really intentional for any type of oil, right? Coming through in there. The biggest oil occurrence you're going to see is at startup, right? Where we starve, we have no load in the display cases at beginning. We're putting our oil in. It takes some while to balance the system. So you have a lot of oil circulating. So we found just going straight at first was a bit of a hiccup. So we threw a few little, maybe, oh, I don't want to call them P-traps, but a little bit of a bend in there to kind of help move that around. And
so when you do that, does that add more velocity to it or slow it down? When you add, because you added
no,
1, 2, 3, 4, we'll say 4 90s in there, 4 to 5 90s.
you got her. Yeah. But remember, we're looking at a picture here. The distance span from here to here is not even 2 feet.
Yeah.
In all respect. So is it going to induce a bit of a pressure drop? Yeah, but we're going to be under a 3-pound pressure drop with this overall design.
This is CO2 we're talking about. Like
you got her. And it ensures that we're having proper mixing, because what's critical here, this design, the guys are working right now, you can see this line coming down. Well, we're on this design using liquid injection on the suction manifold. So AC, we like liquid injection. Basically what's happening is our air conditioning is getting, our suction temperatures warming up past 68 to 72 degrees. We'll inject liquid. We'll go through a expansion valve and inject liquid in there to keep that temperature controlled. It's an inefficiency in the system. Some designs will have a plate heat exchanger, right? So we want to remove those types of inefficiencies. And especially if we have oil pooling, we're going to have oil coming down on this line over here and clogging up this valve. So through some laboratory testing, you'll see our systems. And that's a question we get a lot of times when we're doing startup is, hey, looks like you did this for a reason. And it looks like you put the outlet down here on the flash tank at exactly this location for a reason. Well, yeah, you're right. We did. We came off here. we do the bend. You can see there's a connection here, which is the next page, because this is connected to our backup unit. But this is all intentional. What we want to do is we want to create a good liquid column to feed that manifold. So we have good liquid feed, because what is something all TXVs do not like, electronic TXVs especially, is poor liquid feed. They operate erratically. And you can see that in the graphs, right? We have improper liquid feed. The TXVs are opening and closing, and we're unable to properly maintain display case. So working on a system, you see this is intentional, guys, for all the reasons we just spoke about.
And if you don't know what it does, you ask somebody, you call. Like, you guys got a huge support team that's willing to help answer any of these questions. And I feel more and more technicians need to try to make that phone call after they looked up to try to figure it out and come up. And when you're making that phone call to that, let's say that manufacturer, you're calling Arneg, ask them, don't get them just to give you the answer right away. Say, this is what I think it does, and this is why. Does it do that? Because this is how you learn. If someone just keeps giving you the answers, it's going to take you a lot longer to learn it. So come up with a hypothesis yourself, and then call the manufacturer and ask them, does this work? Because you need to ask someone if you don't know.
Absolutely. And our experience with most manufacturers, and we're a stone throw away from a lot of the guys in Quebec, is they all work really well. And our team, we have a support team. We also have a service team. So if you're stuck, there's a number on the unit, give us a shout. We can respond to you in English or French. So there's no hiccup there.
That's awesome.
So here we go. So now this completes our whole overall design. So here's the backup unit. And I want the team today, I'm going to announce something that is new and breaking with Arneg after we discuss this, because we're really excited about this, and you're going to see this very, very soon. So here is our backup unit, totally critical. Typically is put on a generator. Either we could supply the generator, or it goes on the building generator. So essentially, on a critical instance where we lose power, the backup unit will kick on. We have a plate heat exchanger, and it's going to maintain the pressure inside the flash tank. And then why is this absolutely necessary? We just got back on, we're talking about maintaining pressure inside the flash tank, is because we have all these pressure reliefs here, and our pressure relief typically on a supermarket design is 650 PSI. So if we start to exceed that, we're going to start to lose CO2. So you can see the outlet goes back into our liquid line. Okay, piped a little bit differently than maybe what a lot of people are used to. This is a 1 horsepower pump, okay, and goes through the plate heat exchanger. We're going to run this around about 30 to 32 degrees Fahrenheit, and because we're trying to maintain, here at that moment about 40 degrees Fahrenheit. This is on the control system and not on the control system, because what I'm going to state on that, if we start to lose the flash tank, if the flash tank becomes erratic, and pressure starts to increase, she will kick on, regardless of a power failure or not. This is a safety backup. If you're doing service on a system, you need this. This is critical for any service technician. The backup unit, guys, is not even an option with Arneg. They are fully integrated into the rack. That's why it's up here. We build a shelf for it, slides into the shelf. We pre-pipe it all. Okay, we ship it with a nitrogen charge. Now, here's the big news. More and more, especially for the smaller markets, a building generator isn't there. So the bigger request from us was to provide a small 10 kilowatt generator. In all due honesty, bring in a natural gas line to a generator, or now we talk diesel. It's just not economically smart for a customer. We are working with a supplier right now. We have our first design that's likely going out very soon. We'll be using photovoltaic cells. The cost of the photovoltaic cells with the battery to run a 3 kilowatt backup unit was actually significantly less expensive than the generator. Wow. So imagine the future of this, especially a penthouse. You got photovoltaic cells, you got your battery backup, your generator, if you lose power, your backup unit, if you lose power, will run off the battery backup. And if you got power there, she's going to run a heck of a lot more than, 2 hours. And if, critical time, downtime, we start exceeding past 2 hours, and we got critical problems for all the food within that store. So that's up and coming from us.
That is super cool. I love that.
Yeah, it's up and coming. We got our first penthouse where we'll be doing, there'll be a photovoltaic. So you'll be seeing that soon. We'll share that on LinkedIn. There'll be a news article on the specific customer we're working with, but I think that mindset just complements this total design. You know,
Oh, for
CO2
sure.
photovoltaic,
For
it's
sure. I,
great.
I was talking with a technician about 3 weeks ago, and he just installed a solar, and he's installed a few of them. He says, never had a backup system yet. You know what I
Yeah.
mean? So it's like this is coming with the unit. It's not even an option. It's coming with the unit. So that's awesome.
So I know, Trevor, we're starting to get short on time. I haven't hit on the hot gas, and I'd be more than happy to book another time with you because we spoke about all this good stuff. If we want to do a part two, because I had some
Yeah,
pH diagrams ready, calculations for the technicians, because everything we just spoke about, guys, be more than happy to share with you. Now, how do you calculate that? Pull out your iPhone when you're in the field to get some of those calculations. How do I calculate how much flash gas do I truly have at this moment? It's not that difficult.
I love it. Yeah, I
Anybody
think
can
that's
do
what
it.
we should do because I want to spend some time on that because I think that's very important getting into the hot gas. I know a lot of people south of the border use more of electric defrost and not as much hot gas defrost, but you're going to see it more and more in Canada. It's all I worked on synthetic refrigerants, and now CO2 is tons of hot gas. I think that's a great idea. I really appreciate this. I learned so much today. I got two and a half pages of notes. So if you're listening out there, hopefully you're not, if you're driving or not, when you pull over, get your notepad out, write down some of these tips. All of you that have been on here participating, if you have any questions, throw it in the chat so we can ask Philip while he's here because you can see him and his team designed this cool system. And once again, that air conditioning number right there, I love you having that up there so people understand that CO2 is in air conditioning. I've also seen a post on LinkedIn that there's CO2 in Volkswagen vehicles. You're going to see more and more
Isn't that
CO2 ever.
that's fantastic, isn't
Yeah,
it?
I,
That's
I, I think it's
I
great.
think
I love it.
I think the technology is readily available right now. And as you see, we just announced, like, to everyone here, who's first to hear, we're going to move forward with photovoltaic cells just to the backup unit. So the idea of some of these nuances that we've heard for so many years with CO2, all you need a backup generator, all you need. I think people are getting a lot more intelligent and creative.
Yeah.
And we're working with innovative means to build a holistic system. And given that everything in the industry of what's going on right now and the data we have in our hands for synthetic refrigerants and even capital costs, this may sound like a shock to everyone else, but for us to build a synthetic refrigerant system here at this moment, copper's through the roof. We can buy stainless steel at less of a cost compared to copper. So if in my shop right now, I don't have one synthetic refrigerant in the shop at this moment.
Awesome.
It's 100% CO2.
I love it.
And customers are starting to realize that, so I think the benefits of the federal regulations, at least in Canada, we're talking a lot with the US right now. Um, Installation, regardless of some of the marketplace, is actually a good time for CO2. And I think it's because the technology is readily available and the education from the educators is finally readily available. Like yourself, Trevor, people are really wanting to participate and to get this moving.
I love it. Philip, I really appreciate this. Like again, I've learned a lot. Where can more people learn about you, learn about Arneg if they want to get a hold of you guys, learn a bit more about your systems, about yourself?
Yeah, so feel free. Our website is filled with a whack of information. I think more information than people would realize. Hit us up on our website. It comes directly into us, the directors here. If you're looking at Trevor, feel free to share my contact information. If you want to talk, you want to just speak about it, CO2 over coffee. We do a lot of webinars, and this is something Trevor and I were talking about. We do them in front of machines. And our machines are, we have a bit of a reputation for quiet machines. And I think once you experience that, you'll understand maybe some of the practices that we just spoke about, why the machines run at a much lower decibel. So even if you and your team are looking to do a webinar, we'd be more than happy to get in front of a machine, a live machine, point out the system and give you some good topics that you can run off with.
And so the website would be arneg.ca. Is that correct?
You got her. Yeah.
Awesome. So
Yeah.
everyone,
Arneg.ca, arneg.com is going to hit you on the same website.
awesome. I love it. And Thank you once again, Philip. We're going to do another one of these sessions for everyone because I think this was key. Like I said, I learned so much. I hope a lot of you learned a bunch right there. I will see all of you at the next CO2 Monday with Trevor. Thank you very much, everyone. Thank you, Philip.
Hey, I want to thank you for taking the time to watch this video. I hope you got something out of it, something that you can use in your daily life. If you like this video, hit the thumbs up button, hit the subscribe button, and click the bell button, because when you do click the bell button, it will notify you anytime new videos are released. Also, check out the Refrigeration Mentor webpage at refrigerationmentor.com, where I'll have all the different trainings, upcoming events, the different podcasts I've been on, as well as the Refrigeration Mentor podcast. If you want to check that out on Apple, Spotify, Google, any service provider of your choice. Super excited to see you at the next video. Now let's get a conversation going.